Okay. Welcome back to our third talk in our mini symposia. So I'd like to now introduce Daniel Margalla, who is going to be telling us about accelerating stereoscopic data processing using Python and GPUs on NERSC supercomputers. So that's very cool. And Daniel, please take it away.
Okay, let me share my screen. And can you guys see my screen? Great. Okay, thanks. Yes, my name is Daniel Margalla. I'm a postdoc at the National Energy and Research Scientific Computing Center in Berkeley. And yes, today I'll be talking about how we ported astronomy projects, spectroscopic data processing pipeline in Python to use GPUs on the new supercomputers at NERSC. So the project that we're working with is called the Dark Energy Spectroscopic Instrument, and it's a planned 5-year survey to measure the spectra of over 35 million galaxies and quasars. And the team will use this data set to construct the largest and most detailed three-dimensional map of the universe. And the cosmologists on the project will use this map to measure the effects of dark energy on the expansion history of the universe. And in order to process this data, the collaboration uses the computing facilities at NERSC, and they process the data every night in real time so that it's available the next day for the astronomers to review and update the survey plan. And the team also reprocesses the data every few months using any updates they've made to the processing algorithms for both internal releases and yearly public releases. And one of the requirements that this project has is that it's all implemented in Python. And this is mainly because this is where the skill set of the astronomers on the team in programming lies. And this helps them maintain the software and update it going forward. So the DSI Instrument is kind of a unique telescope. Instead of imaging the light directly on the night sky, there's actually 5,000 robotic arms holding fiber optic cables in the focal plane. So when DSI points the telescope at the sky, they're actually targeting 5,000 unique point light sources in the sky at a time. And they feed the light through those fiber optic cables and spread it out using a diffraction grating and a spectrograph to measure the light in a few different color channels. So this actually creates a very detailed picture of the light signature from each of those objects that it images at a time. So on this slide, I'm showing what one of the raw CCD frames look like. So instead of getting lots of little galaxies and stars in the image, you get a bunch of long streaks, which is the light from each of those individual objects kind of spread out across the CCD. And so the goal of the data processing pipeline is to extract one-dimensional spectra from the raw two-dimensional data that is imaged on the CCD. So if we zoom in on a little patch here, where on the left here, I've zoomed in to show the light from 5 individual objects. And so on the left, we have the two-dimensional image, and the goal of the code that we're working with here is to turn that into one-dimensional spectra. So at each wavelength of light, we want a measurement of the flux, how much energy that object is emitting at each wavelength. And so the team essentially just performs the extraction by performing a two-dimensional forward model of the data. So they come up with a projection matrix to solve for the one-dimensional flux. And so since there's over 4,000 by 4,000 pixels in the raw two-dimensional image, this ends up being very large matrix equations to solve. There's also lots of special functions because the PSF, the model that's used to compute that projection matrix, is stored as Hermite and Legendre polynomials. There's a lot of special functions that need to be evaluated. And in order to properly account for the statistical correlations between all the pixels and the outputs, there's a lot of eigendecompositions of the inverse covariance matrix as well. So that's kind of why those are the computationally intensive pieces of this algorithm. And so the way the team has sort of tackled this problem is to divide the image into tiny patches and extract the spectra in parallel using the large multi-core processors and the compute nodes at NERSC, and also using multiple compute nodes at a time. And the existing CPU implementation uses a lot of NumPy and SciPy operations for linear algebra. There's also special functions that are implemented using numba just-in-time compilation, and the parallelism is achieved using a kind of a single program, multiple data programming paradigm enabled via MPI for Pi for both multi-core and multi-node scaling. And so what we're doing here is since there's a new supercomputer system at NERSC that's going to have over 1,500 GPU nodes, we want to see if we can improve the performance of this extraction algorithm by porting the application to use the GPU. And so the Perlmutter system at NERSC just debuted at number 5 on the top 500 supercomputer list. So at the beginning of this project, we laid out a strategy. So we evaluated the landscape of GPU acceleration that was available to us from Python, and we identified CuPy and the numba CUDA as excellent candidates for us to perform this port, because we'd be able to use the existing sort of implementation and just because the CuPy matches the NumPy API, we'd be able to kind of easily port this over to the GPU. And similarly, we could use numba CUDA, where the existing implementation uses just numba. And then our strategy for maximizing our node utilization is to again keep using MPI for Pi, to use all of the to use multiple CPU processes in combination with the multiple GPUs on each of the nodes, as well as using CUDA multiprocess service to have multiple MPI ranks execute operations on each of the GPUs. We also, I won't go into it in this talk, but we implemented unit tests that compare the CPU and GPU implementations to verify correctness as we kind of refactor and port this over to the GPU. And then another important element of this work is to track performance as we make changes and refactor using a consistent benchmark. So just to give you a short little preview or kind of a look at how we could combine CuPy and numba CUDA and the NumPy API together, kind of came up with this very, very simple example where you can write these CUDA kernels using just Python code, and numba CUDA will compile that down into CUDA code that's executed on the GPU. And on the right here, I kind of show how you can use the CuPy API to create an array on the GPU device, and you can pass that CuPy object through to the numba CUDA code. And then finally, you could use the NumPy API and the kind of array dispatch kind of functionality. So you could use this in some cases to kind of share code paths between the CPU and GPU implementation. So this kind of reduces the amount of code that you actually have to port to the GPU. So here, this call numpy.sum x, even though x is in a CuPy array, this sum is actually occurring on the GPU, even though the NumPy, even though it's a call to NumPy. And then here's an example of porting an actual kernel in the existing DESI code over to GPU. So this is where we had to change something that was implemented using Numba over to Numba CUDA. And I highlighted the lines of code that actually changed here. And so the Numba CUDA kind of has to, you have to write these little wrappers to make it kind of convenient to call from the same code. And some of this is just related to specifics of CUDA programming. But the nice thing about this is that you're still just writing Python. You don't have to write any C or C++ to accomplish any of this. So after we have our initial GPU implementation, we want to measure how it performs. So at the very beginning of this project, the team established a benchmark that we could use to track performance over time. And we performed baseline measurements using the existing supercomputing systems at NERSC that the DESI team was using. And so the baseline measurement that we're going to use for this is the measurement made on the now retired Edison supercomputer. And so the team measured the performance of the existing code was 28 frames per node hour. And so the DESI team uses this metric because it's a measure of throughput, and it's relevant because their kind of computing allocation budget at NERSC is allocated in terms of node hours. And so this kind of gives the team an idea of how much resources that they need to actually process all the data, and kind of do some rough napkin math of how long it would take to process kind of a order of magnitude estimate of the data that they have. So using the Edison system, it would take over 300 node days, and using the Corey-Haswell system, it'd take over 200 node days. So how does our initial GPU implementation perform? Well, this little dot here on the left shows kind of our initial measurement using kind of the Corey GPU test system at NERSC, and it was kind of disappointing. It looks like it's 0. The speed up is 0 relative to Edison baseline. It's actually not quite 0, but it's pretty close. But this isn't really a fair comparison because this was just our initial GPU port, and we're comparing it to a code that's been highly optimized on the CPU systems. So at this point, the next thing we wanted to do was kind of scale up and actually use the full GPU resources that were available to us on each of the nodes. So we accomplished this, as I mentioned earlier, by using MPI to have multiple CPU processes drive the GPUs. We actually have multiple MPI ranks per GPU to make sure that we're saturating the performance on the GPUs. And so on the right here, I have kind of some of these scaling plots that are extremely useful when you're trying to measure the saturation of your node, both CPU and GPU resources, where you kind of measure the performance using a fraction of the resources available and scale up to see how the performance scales. So here, the orange line is just using one MPI rank per GPU. And then when we turn on the CUDA multiprocess service, we can use multiple MPI ranks per GPU. And here we see that we saturate at the green line at 2 MPI ranks per GPU. So if we keep increasing, we don't get any performance benefit. And after a while, we actually see some degradation in performance. So after implementing that, now we're starting to get a speed up relative to our baseline measurements. So this is encouraging. And here I'm actually measuring the performance on 2 systems now. So one is the Corey GPU system in blue, and so that system has an older NVIDIA GPU architecture, the Volta V100s. And at this point in the process, we got access to some newer machines that had the newer A100 GPUs that the Perlmutter system will have. And so those points will show up in orange. And so at this point, we want to figure out how we can continue to get better performance. So we decided we needed to profile our code. And so the way we achieve this is using NVIDIA's Nsight systems. And we're able to use CuPy to add markers to our code. And the CuPy API gives you a few different ways for marking up your code. So you can measure these different regions and label them for the profiler. So here's an example screenshot of what the profiler kind of looks like after running it on the code. And so this view gives us a lot of detailed information, and it also gives us kind of like a high-level, like a timeline view of where time is being spent in our application. So this is an incredibly powerful tool for measuring the performance of the code. So here I've zoomed in on kind of the timeline for a single patch, and you can see that the most of the time is run during this decorrelate step. Actually, 85% of the runtime of the whole extraction for this frame is spent during this function. And we can see that most of it is spent doing a bunch of eigenvalue decompositions. The profile also helped us find unexpected performance issue that we didn't even label with the NVTX markers in this. It's just kind of showing in this missing region here on the right with the question mark. So this was very useful. We didn't even put markers around some things because we didn't expect them to take much time. So this helped us find those, and we were able to eliminate some of those sometimes by just refactoring some of the code. So after identifying this bottleneck doing eigenvalue decompositions, we were able to kind of improve the runtime of this by implementing Cython wrappers for a function, a batched eigenvalue solver in the cuSolver C++ library, and we were able to contribute these back to the open source library CuPy. So this sped up the execution of this kernel by a factor of 2. And then overall, this sped up the runtime of the program by a factor of 1.5. So we can see that our performance improving here on our kind of performance milestone tracker. And so at this point, batching the eigenvalue decomposition was very successful. So we decided to look for more opportunities to batch operations. And so one kind of way I did this was just look for more batched functions in the cuSolver API. And we identified these batched Cholesky factorization and solver, so that we realized that we could use in our application since our inverse covariance matrix was positive definite. So we're able to kind of combine all of these, batch all of the extractions for all these patches together at once using these batched GPU functions. So I kind of visualize here doing a before and after profile, and we're able to kind of group all of those executions of the individual patches together using the batched linear algebra operations down and speed the execution of that up by a factor of over 3. And so now we're starting to really jump up there in terms of performance. And the next thing that we sort of identified by using our benchmark was that the I/O was starting to become a real bottleneck. So in our benchmark, kind of process frames serially, and the time to process a single frame was down to about 6 to 7 seconds using a single node, and the I/O time between the frames was about 1.5 seconds. So you can see here, there's some of the processes are just waiting around, not doing anything, while the main process is writing the results and reading the next frame. So we figured out a way we could sort of work around some of this was by interleaving these I/O operations using spare CPU cycles. Since we had already saturated our GPU usage and we still had spare CPU cores that we weren't utilizing, we're able to utilize some of those by interleaving, by having a few ranks that are just dedicated to writing and reading data. And that was a great way to work around that I/O bottleneck. And so at the end of that, now we have over a 20x speed up compared to our baseline measurement. And for comparison, in those kind of back of the envelope numbers before, where it took over 300 Edison node days to process a full data set, now this is down to just a 15 Perlmutter node days. So for DESI, the transition to GPUs on Perlmutter will shorten the time it takes to process years worth of data from weeks to months down to hours or days. So some of the lessons that we learned, which we think would be useful for any scientific teams that are looking to port their data processing over to GPUs, is that just making better use of NumPy is extremely powerful. It'll help both your CPU performance, and because many of the tools used for GPU acceleration are based on NumPy, it would also help there as well. We're also able to kind of effectively leverage, kind of extend our use of MPI for Pi with the CUDA multiprocess service to ensure that we're actually saturating our GPU usage. And another way of keeping the GPU busy is just to kind of batch as many array and linear algebra operations as possible. The other very important thing is to actually profile your code to identify where the bottlenecks are. And so we made heavy use of the Nsight Systems tool, but even just more basic tools like the C profiler are also helpful for this, this sort of thing. We also found that it was useful to redo the hyperparameter studies every once in a while. So choosing the optimal kind of patch sizes and any other hyperparameters that you have, the optimal values of those can vary as you refactor different parts of the code. So it's useful to redo those every now and then. And some of the other things, just running sometimes Python on HPC is a bit of a stranger. A lot of my colleagues, work in C++ and Fortran, or the Python users are kind of the odd ones out. And there's just a very deep stack that you have to learn to get a lot of performance out of the system. So you have to make sure your programming environment is set up right. You have to understand the job scheduler, and sometimes it's useful to use containers and understand MPI and OpenMP. So there's just a lot there to learn. And we also along the way found some interesting things, like we identified that I/O on one of the file systems available at NERSC, there were some issues. And so we're able to work around this because we could use a different file system, but it's still kind of strange issues like this pop up every now and then. And some of the next steps are integrating this with the actual production pipeline. And also we're exploring the code for other opportunities. So here on the right, I'm kind of showing a few of the other steps in the data processing pipeline. So I focused mostly in this talk on that green bar, the extraction step. And so there are other steps that could benefit from GPU acceleration as well. And then as we scale this up, we're kind of curious if we're going to run into more I/O issues at running at scale. So thank you very much. I'm happy to take any questions.
Thank you very much. So please do keep those questions coming into Q&A. And in the meantime, I would abuse my chair privileges and would ask you the question of how much of this work can be generalized? So this is focusing on DESI specifically, but would it be easy to transfer it to other surveys, either upcoming or reprocessing previous data sets?
Yeah, I'm not an expert on the tools used by other spectroscopic surveys, but I know the approach taken by the DESI team has been to try to kind of keep the different steps of the pipeline. Like, for example, this extraction code is in its own GitHub repository. So in theory, this would be able to be used by other projects that had a similar sort of data set.
Thank you. So I see there is some comments going on the chat. So I would invite Todd and you to have that discussion going maybe on Slack or as a follow-up, or I'm happy to invite Todd on the stage if they want to.
Okay, I see there's a question from Tom. Are the streaks due to sky movement? So let me share my screen again. So the vertical streaks are the actual light sources that the team is trying to target. The other kind of random streaks are actually due to cosmic rays that are captured by the CCD. And so that's kind of noise. And there's earlier steps in the pipeline that tries to identify those cosmic rays and kind of create a mask to filter those out.
Okay, so if there are no more questions, then I would like to thank Daniel again for the very interesting talk, and would invite everyone to follow it up on Slack if needed.
Thank you.